Welcome, wonderful physics people. We're going to be defining work and energy today, so let's get into it. First, work is a very specific definition in physics and really all of science that oftentimes when people are talking about work, they use it incorrectly. So we're going to free up a little bit of your mind of how you commonly think of work and get to a more specific definition of work. So energy is defined as the ability to do work. However, we need the definition for work in order for that to make any sense. Work is simply defined as the transfer of energy. Transfer of energy. Well, now it looks like we're getting into circular logic here because that gives us in terms of energy, but then our definition of energy is in terms of work. But we can write it like this now, that work is the change or a delta of energy there. Okay, cool. So let's keep going and we'll figure out this little problem here. If the work is done is positive, the system is gaining energy. And if the work done is negative, well, then we're losing energy. So it's a little bit different than what we've seen before. It is a direction, but it's not like a physical direction. So before, when we had displacement, velocity, and acceleration or force, these things told us I'm going to write in physical direction, which is a direction. But now it tells us whether energy is flowing into or out of the system, but that still is a direction, but it's a little bit different conceptually maybe. So if we drew our system here, where a little circle where we write in what the system is, if I had an arrow that's going into this thing, that would be maybe like +3 boxes we'll make up here like we've done before. This would be something that's flowing, energy is flowing into the system. Conversely, I might have something that's like transferring energy out of the system, maybe like a -3 boxes there. And this arrow that's going from the system out of the system, this is showing the energy flowing out of that system there. So we've actually kind of seen that before on worksheet 1 and worksheet 2, but that's what's actually going on. Okay, so now let's figure out what work actually is, and I'm going to stick with green because I like green. To figure out the meaning of energy and work, we need to think about what having more energy means to us intuitively. So let's think about like an object moving. We can intuitively sense that it has more energy than if it was just at rest. This type of energy is called kinetic energy, right? So we have energy that's in motion, just like that skater in the skate park simulation had more energy when he was in motion. So the symbol of kinetic energy is K, or KE in your book. We oftentimes don't use KE when we're writing it out handwritten because that sure looks like it has two variables there, K times E, and that could get quite confusing. Your book uses a different font for KE to show that it's its own separate thing there. It's pretty hard to do handwritten there, so most people will just do K. Well, the larger the system's mass, the more or less kinetic energy you think it has. Well, let's draw a picture and kind of see what's going on there. So if I had some sort of mass, here's a box and it's got some mass inside there, and let's put 4 representative molecules, you might say, of mass there. And if we had this box maybe moving to the right at 20 meters per second across a frictionless surface or something like that, or maybe it's in space, and that would be even better. You could go, oh, well, these guys they're all moving 20 meters per second to the right. Each one of those has some sort of kinetic energy. Well, what if I had let's say the same size box here, and maybe in this same size box, I'd have a different chemical, different molecules here that are more tightly packed. Oh, I'm going to do that last one in a different color. And so I can fit, let's say, twice as many particles within the same space, assuming that these are all the same massed particles, so we can simplify it a little bit here. If I had this thing going at 20 meters per second, which one of these would have more kinetic energy? Well, this one down here, if they're all the same amount of mass for each little particle that I've drawn there, this one's got twice the amount that are going to the right at 20 meters per second. So wouldn't it have more kinetic energy? Maybe it would be twice the amount. We're not really sure yet, but it would definitely have more because you got more things that are in motion. So that kind of intuitively means that the larger the system's mass, the more kinetic energy it has. The larger the system's, that's the larger the system's speed. So we could do the same thing, but with speed there. And the larger the system's mass, the more kinetic energy it would have as well. All right, so now we got to get some formula for kinetic energy, so we can actually figure out, is it double, or maybe it doesn't go up linearly. We're not sure yet. We'll figure that out, and we'll define that here. So if you want to change the object's speed, it's going to have to accelerate. And so from Newton's second law, we know that, hey, the sum of the forces is equal to mass times acceleration every time. And you know that to make an object accelerate, you got to put some sum of the forces. You got to have that that's not equal to zero. You have to apply an unbalanced force, you might say. You could say this in many different ways, unbalanced force. And we know that the larger the force, the larger the acceleration. So then we'd get a bigger, smaller change in velocity, bigger change in velocity. So wait, that means that if we have a bigger change in velocity, we'd have more kinetic energy. And so now would more or less be work done if I had this bigger force? Well, work is that change in energy. And so if I'm talking about more kinetic energy, because it's moving faster here, so it's going to have more work done on that thing. Okay, cool. Defining work in our minds here and figuring out what that means. And so then the kinetic energy is going to be larger than as well, as we were describing. So besides changing the size of the force, we can also consider the distance through which it acts. Wait, hold on. The distance through which it acts? Why is distance in there? Why not time? What about time? We've looked at time many different times before as well. And why wouldn't that be a thing? Well, here's a simple way to think about this. Imagine you're probably sitting right now on a chair. So let's draw a chair. And I'm not the best drawer in the world, but I think you get the idea. You're sitting on a chair here and you go, hey, chair is sitting on the floor. And you go, hey, look at these legs here that are touching the floor there. Do they have any forces potentially going on there? And you'd say, oh, yeah. What? There's like this, on the chair here, there's a big normal force on the chair there. You might be like shifting left or right, but the chair might not actually slide against the floor, right? You might put some sort of lateral force, left or right, on that chair, but maybe it doesn't actually slide. And so maybe you try to slide it forward, but it doesn't actually slide forward. What's holding you back there? If you're trying to slide, if you're pushing it forward, you're trying to scooch in so you can eat your meal there, but it doesn't go forward, something must be pushing back. What force is pushing it back? And you'll say, oh, that's going to be static friction there. Well, now wait, hold on a second. Let's think about friction and what we know about static friction. How much heat is generated or transferred to heat? How much energy is transferred to heat with static friction? You'd say, well, zero. Static friction does not cause anything to heat up. We've seen that before in worksheet 1. And you go, well, why not? Isn't that friction in this case applying over some time? Yeah, it's applying over some time. But then, wait, let's redefine it in terms of work. Is this static friction doing any work? Well, is it transferring energy? Is it transferring energy to, in this case, thermal energy? And we say, well, no, it's not transferring energy to thermal energy. So then it means it's not transferring any energy. And so then it's not doing any work. So static friction, we can redefine that, does no work or zero work. Let me write work better. So static friction does zero work, no work at all. But it's operating over some time there. Well, maybe work or the change in energy, maybe that doesn't depend on time that these forces are acting. Maybe it depends on something else. And you guessed it, maybe it depends on the distance. And if we look at this example with distance, well, how much distance is static friction acting through, you might say, on this chair? Well, zero. Yeah, so there's like zero distance, now let me write it, zero distance that static friction acts through, and therefore, or this implies, well, I guess I could do therefore actually. The three little dots, if you remember, is the therefore symbol. Therefore, there is zero work, let me write a better W than that. The work due to static friction, and actually I'm going to go write that as static friction. The work that static friction does is equal to zero. Okay, so, okay, all right. So now we can start thinking about some of these other cases, maybe not from forces that are acting over some time period there, but instead forces that are acting through some sort of distance there. So that means that the force applied through a larger distance is going to do more or less work. And you go, oh yeah, the one that does a larger distance will do more work, and if it was a smaller distance, it would do less work. Okay, moving on. So besides the force and the distance that which they're applied through, there's more to the story than just this. What about which way that you're pushing that thing, the direction of that force? Imagine that we have this block that's sliding across a frictionless table at a constant speed. And whenever I read constant speed, I also recognize that the acceleration must be zero. So then, okay, cool. So it's already sliding across to the right there. If I apply a force pushing the block to the right, okay, so let's go and push this thing. So I'm going to go and I'm going to put my hand on it, or maybe I'm going to go and like actively try to push this thing. Maybe it's like a big shopping cart. Maybe my car ran out of gas and I got to push this thing, and I'm going to put a big normal force, well, I'll write it like this, a big normal force in this case, on that thing. If I keep pushing that to the right there and I keep applying this big force there, you say it's going to get faster, slower, no change in speed? Clearly it's going to get faster. So its kinetic energy is going to increase, decrease, not change. It's going to increase, right? It gets faster, and therefore it has more kinetic energy. It's got more energy in motion, is another way to say kinetic energy. So if you apply a force pushing it to the left instead, well, let's change this diagram here. So now I have the shopping cart, or the car that's already moving to the right there, and I go, oh, let me push the block to the left. If we think about a shopping cart, I kind of like the shopping cart example. If we think about a shopping cart, because we do this all the time, I could still be standing on this side because I'm like gripping the handle there, right? And I could put a force to the left there by pulling backwards on that handle of the shopping cart there. So I could put, and since my fingers are wrapped around that bar of the handle, then that would actually be a normal force there. So if I put a force on the left, then that shopping cart's going to get faster, slower, no change in speed. Oh yeah, it's going to get slower here. And so its kinetic energy will increase, decrease. It's going to be decreasing because it's going to be not moving as fast. All right, now if you apply a force pushing straight down, what's going to happen here? Okay, so let's go change this scenario here. So I'm going to be a giant in this case, I guess. So I'm going to go, I'm going to be a huge giant. It's a small little block now, and I'm going to go ahead and I'm going to, got my elbows here, and I'm going to try and push straight down on that thing. Get my other arm in there too. That's a wonderful drawing. This is going to go in the Met Museum. So this thing is going to have a huge normal force going down. Well, as I'm pushing only straight down in this frictionless surface here, so friction's not going to be increasing or anything like that, just my push, think about just my push, me pushing it straight downwards into the table there, is that going to cause it to get faster or get slower? No, I'm not pushing it with it nor against it. Instead, I'm pushing like perpendicular to the way that it's going. Oh, that sounds like a circular motion a little bit. So it's not going to have any change in speed, and so then its kinetic energy won't change as well. Now, if a force is applied at an angle to the motion, so not straight on or back or even perpendicular, but some angle like we've seen below here, then now what's going on with this? Well, I look at this force, and immediately you should be saying to yourself, oh, I should be doing component vectors for that thing, right? And so let's go ahead and put in some component vectors there. And okay, so now we got a force that's going along that displacement or distance, or it's really a displacement. And we have a little bit of the force that's going perpendicular to that as well. So now, is this going to, increase or decrease in speed or kinetic energy? Well, let's get into that. Now, only a component of this is parallel or perpendicular to the distance. And so the thing that is actually going to cause it to change in kinetic energy is only going to be the part that is parallel to that distance there, as we saw in that previous example. The only thing pushing it in the direction or against its direction that it's currently going or can go. So we drew in the component vectors already. Now, if we call the angle between force and the direction of motion theta, then the component will affect the energy is equal to, we already know that this guy over here is going to be F cosine theta, as we've done many times before, and this guy over here is going to be F sine theta. Okay. Now, I'll go define theta in the next page here. So the force that actually affects the energy here in this case is going to be F cosine theta. So now we know that we care about both the components of the force and the distance it pushes through, or really displacement. Then we get an equation for work that it's the F times the cosine of theta and then times my delta x there. And I'll put some parentheses around that so we don't get confused there. So, okay, well, what if theta was 0? Well, then cosine of 0, what is that? Yeah, that's right, that's just 1. So now we have force times delta x, and everything's hunky-dory, just like we saw in that first example. All right, moving on. What if the force pushes against the direction of motion, but not directly against it at some angle there? Draw on the force components as we know. And so if I see any force or vector, and that's not really horizontal there. So I'm drawing one horizontal vector. That's a little bit wavy of a line there. And one vertical one there. And now I go, all right, now how much is actually causing this to speed up and slow down? Well, I'm going to label these things as we know. F cosine theta, F sine theta. And we didn't actually define theta in that last page, but let's go ahead and let's do that here. Draw in your theta. And I'm guessing that you probably drew it in right here. Let's think about that for a second. That angle is, I don't know, let's put a number to it. Let's say that the angle is 30 degrees. Now, when you take this force here, which is at some weird angle, so we just have the magnitude of this force here. Let's say the magnitude of this force was 200 just for a second here, 200 newtons. Well, the magnitude is just 200, and the size of it is just 200, and it's going some weird direction there. And if I did the math to get F cosine theta, I'd do 200 times the cosine of theta. Would that give me a positive or negative value? 200 times the cosine of 30, that'll give you a positive value, except this blue vector right here is positive or negative, you'd say. My coordinate plane, my Cartesian coordinate plane, which we're assuming, unless we are defining something differently, we're always assuming here that we have a positive over here and positive up there and negative down there and negative over there. So we know that the F cosine theta, we expect it to be negative. Why doesn't the math come out to be negative? Maybe we defined theta incorrectly here. How else could you define theta so that the math actually works out? Because math all works out every time. And it's only when we have a misunderstanding that it doesn't work out. How else can you draw on that theta? So if we define it between the displacement vector, delta x, and that force there, if I start it on the displacement vector and then measure around here to the force vector, that is going to be my theta. This is theta. Now, if we think about that, you go, oh, that's more than 180 degrees. That's somewhere, in that third quadrant. Remember, this is first quadrant, second quadrant, third quadrant, and fourth quadrant, just so it's easy to reference them. That's somewhere in that third quadrant, and let's say that it's something about like 220 degrees, just making that up. Now, take your calculator, if you haven't already, right? And we said, hey, in our example here, this is 200 newtons. Well, now do F cosine of 220, so 200 times the cosine of 220, what do you get? Don't forget to be in degrees, because it says degrees there. Yeah, you get a negative value. Hey, and that's exactly what I expected. Oh, okay, so you're saying instead of using the reference angle, like oftentimes you use the reference angle so often you even forget that it's a reference angle. Instead of using this reference angle, that's that little guy in there, if you use the whole angle, well, the sines usually work out there. Okay, there's a couple exceptions to that, but that's the way that it's actually defined there. Okay, cool, sweet. So the 200 was just an example there. All right, so then the cosine will be negative when we go and do that, as we were describing up there. I'm going to stick with red. Therefore, the sign on the work is going to be, wait, hold on, we said work was the f cosine theta times my delta x. Well, delta x is positive, and then f cosine theta, that's negative. So then this thing must be negative, and the system will lose energy, lose kinetic energy. Does that make sense? Remember, I'm pushing it this way. And you should say, oh yeah, when I'm pushing it like against the motion, this f cosine theta is going against the motion, so then it's going to slow down like in that second case that we saw on the previous page. Okay, cool. So it should lose kinetic energy, and the only way it loses kinetic energy if work is going out of the system. And remember, when work is negative, that's going out of the system. So what does that look like on our LOL diagrams? Well, that looks like if I have my system here, draw an arrow that's going out of the system to show that energy is leaving that system. How much energy is leaving the system? Well, we don't have numbers yet, but it might be like 3 boxes like we've done before. The idea that energy is leaving the system. This energy that's leaving the system is work. So it's actually, this work is negative 3 boxes, you might say, right? Because work is the change in energy. And so then anytime that you were transferring energy, you were doing work. Right? Another way to say this delta E is transferring energy. All right. I was kind of summing everything up here. So since energy is defined as the ability to do work, and work is defined now as the force applied through a distance, or really displacement as we've seen, we can now get a new definition for energy. Energy is the ability to apply a force through a distance, and work is the amount of energy that is transferred in or out of our system, and the part of the force parallel to the motion multiplied by the distance it pushes through. And, going right on this, another way to write it that sometimes is simpler for some people is that work is defined as the, again, force that is parallel to that motion. So I've seen it written like this, and I oftentimes think about it and write it like this as well. If the cosine theta is throwing you off there, well, think about it like this. F parallel delta x. Well, force, parallel to what? Parallel to the other vector here, the other variable there, right? Remember that all equations, they all work in reference to themselves. So this force and this delta x have to be related somehow. And then this force parallel, it's got to be a force that's parallel to this other thing, that delta x there. And so then if you go, oh, okay, great, I can do the component vectors up here as we've done before, I can do those no problem. Well, then you just go, oh, anytime that I have these different forces there, I just go, oh, it's just the parallel one multiplied by my delta x there. Okay, now this thing that we've done here, the work is my f cosine theta delta x. What we've actually done is we did the dot product between a force and delta x. Now this dot product, which I'm going to reference this dot as a big red thing, you might say, well, that's just multiplying. And it is, but it's not. So that dot product there, let me write out dot product. This is a dot product. This is a math thing. And it just means that here, if I write this particularly in the correct way, this force is a vector. It's got a direction. this delta x is a direction as well. So notice I'm not just multiplying two numbers against each other. I'm actually multiplying two numbers and their directions with each other as well. And so now how do you multiply directions, you're saying? Well, that's exactly the problem or the complexity that we have here. And that thing is called the dot product. That's how we resolve that. How do we resolve that? We did that already. To do the dot product, it is just the first vector multiplied by the cosine of that angle between these two vectors there. So everything that we just did with the component vectors, with saying, and let me write it down here as well, of saying that it's just the force that is parallel to my delta x, that all is resolving this dot product here. That's how you actually do that. So I could have any two vectors, and if I needed to multiply any two vectors together, it's really a dot product. And every time, it's just going to be the bits that are parallel to each other that you're actually multiplying. So, okay, cool. So that's a fun math thing. Maybe you've done that in math, and if you haven't, well, no big deal. It's just that stuff. Okay, so then we have two different formulas here that the sum of the work is equal to my change in all of the kinetic energies, because maybe I have more than just one force that's causing it to speed up or slow down, and maybe I have multiple ones, so then it's the addition or the sum of all of those individual works or forces. And so then I have work as F dot delta x, as we were talked up there with the dot product, and we know that the dot product to resolve that is just multiplying by the cosine of theta between those two vectors, or just going, hey, we need the components of there, we need the bits that are parallel to one another, and you multiply the ones that are parallel to one another, and that is the dot product every time. So by the way, what are the units for work? Well, hey, let's go do it with units here. Let me do that in a different color. So if we did this with just units, the unit you'd expect for force to be in is newtons. And the unit for delta x, meters. So the unit is a newton times a meter. Huh. Well, that's kind of weird. So I can transfer energy in 300 newton meters. That's a little bit weird. Notice it's not a newton per meter. Careful, a newton per a meter would be written like this. This is a newton meter, would be the proper way to say that, or a newton times a meter. Well, we use energy a whole lot, and saying newton meter every time, two words, we get a little bit lazy. And we recognize that it's a really important concept, so we define a new unit, and I bet you could even guess that. A lot of people have already. A newton times a meter we define as a joule. After James Prescott Joule, and he first used a wonderful little device. He did many different things, but one of his little devices was converting mechanical energy into thermal energy and proving that as you moved things around, in his case water, as you moved water around, it actually heated up that water. So back in worksheet 1 supplement, you had somebody jumping into water, and you did an LOL diagram of when they came to a stop in the water, and it said, where did the energy go? Yeah, it actually went to moving those particles of water. As you're jumping into the water and you're pushing that water along there, you're making those molecules move, and they're going to bump into each other more and more and more. And so then that is going to cause them to vibrate at that molecular level a little bit more, and that's what we call heat, and that's what we measure that to be. And I put a link on my website of the Wikipedia article and the picture of the device that he used to do that in a little description there. So go check that out. James Prescott Joule. A little side note here, whenever you're writing the unit joule, it's a lowercase j. If you do a capital J, you were talking about James Prescott Joule, and that's how we differentiate between those two. So it is a lowercase j when you write out joule. However, this is the confusing thing. If I said, hey, it's got 300 joules, you might also equally say, oh, that's lowercase j. Nope, that's a capital J for the unit there. But when you write it out, it's a lowercase j. A little bit, not a big deal, but a little bit weird. So what would be the units for kinetic energy then? Well, if any energy is in a joule, then kinetic energy is also in a joule as well. Okay, cool. And careful here, it's not a Newton meter. Okay. Last little bit, let's relate it back to things we've done in circular motion, and we got a ramp down there as well. So to solve problems in work and kinetic energy, first draw a force diagram. For each force, ask yourself if it is doing work. Does it have a component that's parallel to its motion? If so, you put a work term on the left side of the equation for it. What equation are we talking about? We're talking about this one right here. The sum of the work is equal to my change in kinetic energy. And so then if I have, I put different work terms here. Maybe I have a normal force, maybe I have a frictional force, who knows what I have, and then that's going to be equal to the total amount of change in kinetic energy of that thing. And this is a capital K here, and that was a bad capital K. But remember, kinetic energy is a capital K because that we don't know this. We don't know about springs yet. But there's another lowercase k, so draw that one as a capital K. All right. If the term will be positive, if the force pushes with its motion, negative if it pushes against the motion, as we've seen, and we sum these things together, and that's the change of the kinetic energy there. So now we got this classic example, the stopper on a string is whirled in the horizontal circle, like above your head. Go ahead and take an object and whirl it above your head in a safe manner. So let's take that object, in this case maybe a stopper or a ball or whatever it is that you just spun there. And we're looking on the top-down view. Top-down, I should say. Stopper moving clockwise, that means it's going this direction here at a constant speed. Oh. All right. So draw in a velocity vector. You should be working ahead of me. I should give you a little time here. Draw in the force, and we're assuming there's some sort of string there. You go, oh, yeah, there's a force on this thing. Let me do force in a different color here. There's a force on that stopper there, and the force is going that way. And you'd say, yeah, that's a whole bunch of tension there. And so now we go, hey, which way is it going? Well, what's its displacement? Because I want to know how much work it's done. And I know that work is just my force, and let me write it like that, force that's parallel to my delta x. Well, where's my delta x? Well, if it's moving to the right, well, hold on a second, what is velocity again? Do you remember what velocity is? Let's take a trip back down memory lane here. And you go, hey, if I made some graph here, I might be able to see velocity. This is where we first saw velocity. If I had some graph and something was moving at a constant speed, it'd look like that, right? Where was velocity on that graph? You said, oh, wait, hold on. The slope of that thing is velocity. Well, now slope is the change in something over the change in something. It's a change in, not y and x, but instead this case, position, x, and time, t. So wait, hold on. That means that velocity is delta x over delta t. Oh, I remember that now. And now when we look at that, we go, wait, I put its velocity vector, so which way is it changing its position only at this point right here? Can you draw it in? You go, whoa, right at this point right here, it is moving that direction, so its displacement vector is that way at this point right now. Now I know that that displacement vector is going to change each time you go along here, just as my velocity is changing. My velocity is changing every time as I go along here, and it's always tangent to this object's path here. And that's how I know that the displacement is going that direction there as well. So it's only for this infinitesimally small time that it's going just tangent, that its displacement is just tangent there, because it's going to change slightly in that next state there as well. But right there, it's going that direction. Now, if it's going that direction there, well, how much of this tension is doing work on this stopper there? Well, the tension and the delta x, what's their angle? I could even draw in that angle. Their angle would be like this. And if that confuses you, go, hey, what's the complementary angle in here? Well, that complementary angle is 90 degrees, yeah? And so then you go, oh, the cosine of 90 degrees. What's the cosine of 90 degrees? Isn't that 0? And so you go, oh, well, I want to know work. That's f cosine theta delta x. And you go, well, cosine theta is 0. And so now how much work is that tension doing on this block? And you'd have to say, well, it's 0 times everything. It's just 0. So then it's doing 0 work Question mark? Isn't the tension actually doing something, though? Isn't it changing its direction? So it sure seems like the tension is doing something, so shouldn't it be changing the amount of energy that's in that system? Well, let's think about the kinetic energy for a second. How is this thing moving? Moving around in a circle? Is it accelerating? You should say yes. Is it moving at a constant speed? Speed, not velocity. Is it moving at a constant speed? And you'd say, yeah, well, it lists that it's going here at a constant speed, and I know that I could take any object and actually spin it around at a constant speed there. So if it's going at a constant speed, tell me something straight away about its kinetic energy if it's going at a constant speed. I know that the kinetic energy must be constant if it's going at a constant speed. We're also assuming that the mass isn't changing of this object that we're spinning around here. I guess something could be flying off of that thing. Let's assume that it's not in this case. So if the mass isn't changing, and the velocity is changing, but only in direction. So the number that goes along with velocity, which is its speed, or the magnitude of the velocity, which is its speed, if that number is constant, then the kinetic energy must be constant. Oh, so now if the kinetic energy is constant, now how much is this tension transferring energy? How much energy is that tension transferring to that stopper there? And you'd say, well, yeah, it'd have to be zero. So the kinetic energy would have to be constant here, just as we said before. And so then that makes a little bit more sense that the amount of work that the tension is doing on the stopper is actually zero. And it is zero. What is that tension doing if it's not increasing or decreasing its kinetic energy? Well, you might say that the tension is changing the direction that it's going. And I would agree with you as well. It's doing something, but we can't say that it's doing work on an object. And here's one case where I'd say that most people, when they describe work and what work means outside of a science context, they describe it inherently incorrectly, where they would say, oh, this tension here is doing work on the stopper. That's not actually true, because it's not changing the amount of energy of that thing. And people, we as a society generally use things, many people use things incorrectly, at least here and there a little bit, because a lot of people don't fully understand what it is that they're talking about. Well, now you do, so you won't be that person who propagates that misunderstanding along the way. And that's the other thing. We always pass information down from generation to generation. But if you pass information that is not true, that is maybe misinformation, then it misinforms the next generation, and keeps going on and makes this generational problem. So fix the generational problem. Hey, you have the power in your hand. Okay, last situation here. Imagine the following situation. We got a spring here. It's all cramped up there, crushed, you might say. And it's pushing on this block here, even though there's a little gap there. There shouldn't be a little gap, sorry. So this spring is going to be pushing on the block, and the block is going to move up that ramp, and it's on some 30-degree angle. So when I let go of the block, the four forces that act on the block, we should do a free body diagram. That's a good idea. So I'll go define my system. Since I have a bunch of objects in here, notice this is why defining your system is so important. Because it's on a ramp here, I'm going to do my free body diagram as a box. You can do it as a dot as well. I find, especially on a ramp here, since I got to draw forces that are parallel and perpendicular to it, that it's much more useful to write, to draw the box here so that I can easily draw that this guy is normal or perpendicular to the bottom there. And then I got to be careful with gravity here. Gravity goes straight down towards the bottom of the page there. There's my mg. Now the spring is pushing it up the ramp, and it's pushing it, from that surface right there. So I started on that surface, and it's going that way, and that's like some sort of normal force. But now, wait, hold on a second. I got two normal forces here. I should put subscripts on them. So this is a normal force on the block by I'll put R for ramp, and maybe this is on the block by the spring there. I'll comma separate them. And then one last force, I go, wait, hold on. As it's going up, isn't it rubbing across that surface there? So I'm thinking to myself, on that surface, maybe there's some sort of static friction that's going on there. Okay, cool. So now let's go and analyze all these guys. I'm going to go and on this diagram, draw in my displacement vector so then I can easily look at this displacement, which way it's going relative to these forces. So let's start with the normal force, and here we're talking about the normal force for number 1 here on the block by the ramp there. And so then that guy is perpendicular to it, so it's got to do no work. Gravitational force, oh wait, hold on, we didn't put in component vectors, and hopefully you were yelling at me there to put in component vectors. And so then I go and put in some component vectors there, and I'm doing that because it's on a ramp here, so you might say I'm rotating the coordinate plane, and I'm calling this the parallel and perpendicular direction, so that it's going, I have axes that are going along the direction, along the displacement vector that this thing is moving or might move there. And we're going to define this as positive and negative there. And so now we look at this gravitational force, and I see that we got theta that's right in there, and we can prove that via geometry. And so then this guy over here is mg cosine theta, and down here is mg sine theta. And so the gravitational force must do, well, it's going, this guy is going, you know, the first one, mg cosine theta, is going perpendicular to it, so it does no work. This guy is going against it, so it's going to do negative work. Now the spring force, that's this other normal force on the block by the spring, that's pushing along the ramp there, up the ramp, same direction as the displacement vector, so then it's going to be doing positive work. And the friction force, going directly against it, so it's got to do negative amounts of work. And that's it. Have a beautiful day.